thank you for all having me today. So, I'd like you to imagine that you're given a task at your job, and that task is solving a Sudoku. So, actually I'm just going to, I think maybe it'll work a bit better if I go back in. Let's see. Yes, so solving a Sudoku. So for those of you that don't know, a Sudoku, you just get given some numbers, so that maybe the numbers are black, and then the puzzle is just to put the numbers 1 to 9 in every row, in every column, and in every square. So, has anyone actually tried to do this before? Has anyone written a Sudoku solver? Yes, so maybe this chap over here. So how did you do it? What was your approach?
Well, I tried to, you have to solve it a number of different ways. There's like a naive approach where you can just add them up and look for gaps.
Yep.
And you start having to do projections, just like you would in, say, a game of chess or something like
Yep.
that. So it's fun. You really scale different things.
Yep, so as this chap said, I mean, if you just brute force it, it's really not tractable because, I mean, you have 81 squares and there are 9 possible combinations in every square. So you have 81 to the 9 possible combinations, and that doesn't really work. So you end up writing quite a complicated program which uses the constraints somehow and maybe does some backtracking where you have to choose, I think I might be able to put a 1 here, and then I try and solve it with a 1 here, and it might not work, so I might have to change to a 3 or something like that. And I think it's quite hard to do. And I think there is a better way of doing it than that, basically. And I think we can use logic to do it. So specifically a form of logic called propositional logic. So this is a definition of what a proposition is, basically. And I don't think it's that helpful, really. So maybe I would use this one. So all propositional logic is just a way of talking about things that can be true or false. And we just build a logic out of just true and false. It's kind of like Booleans in a programming language, if you had a programming language just with Booleans, really. So we start off in propositional logic with these things. So these are just atomic propositions. So they're the simplest possible things that can be true or false, basically. So the first 3 here are just kind of facts about our world, about life. And then maybe we have the constant true. So that's the atomic proposition that's just always true. And the constant false, which is always false. And then maybe we also just have kind of a cell. So this is something that can be true or false. And we decide what meaning to give it based on the problem. And then we can take our atomic propositions and we can build formulae out of them, basically. So we can build a formula not A. So if A is a formula in propositional logic, then not A is just the formula that's true when A is false and false when A is true. We can have A and B. So this is just the formula which is true when A is true and B is true. A or B, true when A is true or B is true. And finally this last one, if A then B. So this one is the only one that's a little difficult to understand, but I think it's not too bad. So what's the meaning of this statement? Well, it's true when it's more than 30 degrees outside and when Neil went to the shops. But it can also be true if it's just less than 30 degrees outside. So, I mean, that's kind of an arbitrary definition. So it's true when the right-hand side is true always, or if the left-hand side is false. And yeah, that's kind of arbitrary, but it makes this connective quite useful, basically. So you might be asking, how is this all relevant to Sudoku? And the answer is that basically at the moment it's not at all. But that's okay. So to solve Sudoku with propositional logic, first we need to think about kind of a set of facts where if we knew whether they were true or false, we could extract a Sudoku solution from them very easily. So first we're thinking about kind of which atomic propositions do we need. So the ones that I've chosen, I mean, I'm not saying that it's the only way of doing it, but this seems sensible, I think. So we just, the facts are whether the cell in row I and column j holds the number k. So we have, and we will write x, I, j, k a bit further down the line. So we might have x115, and all that means is that there's a 5 in this cell. So if it's true, there's a 5 in the cell, and if it's false, then there's not a 5 in that cell. So this is kind of what it might look like in, oh wait, hang on, sorry. So I can show you with the library that I'm using how this works. So I can, it's okay, because, perfect, okay. So if I'm very careful here, maybe it'll work. So I'm using a library here called CafeSat, and what we can do here is we can just define a few variables like this, and then we can write a formula, maybe. And all we do is we just build up a formula in memory, basically. And it provides nice overloads for ands and ors and not. So you just write what looks like a normal Boolean expression, and it builds the formula up in memory. So, I have to do this again. Terrible. In Scala, this is what I just was talking about before might look like. So, a proposition for every row, every column, and every value. So yeah, so we just have for all the numbers from 1 to 9, for row, column, and value, we generate a propositional variable, and here we just give it a name. And we also store the row, column, and value, just so we can kind of select different formulae out, different propositions out later. Yeah, this just has that formula. So next, what we need to think about is what constraints kind of affect a single square, because we've got the atomic propositions, but we need to encode the rules of Sudoku in our language. So first up, we need some helpers. So this just takes a sequence of formulae and puts an and between them. And this one, any, it takes a sequence of formula and puts or between them. And then finally, this one, often it's quite useful to say something about kind of every combination of row, column, and value. So we might want to say that the formula for every cell implies some other formula. And this just lets us do that, basically. So I think maybe the first rule of Sudoku is if we have a value in row I and column j, and it's k, then we can't have another k in the same row. So that's just from the rules of Sudoku. I think you can argue that. So this is how we might express this in propositional logic. So this is in the first column of the row. If we have a 1, then it must not appear in the second column, the third column, or the fourth column up until 9. And the same if we have a 2, then it must not appear in the second column and third column, and so on. And then if we have a 1 in the second column, then it can't appear in the first column or the third column, or so on. So in Scala, we can kind of encode this using the helpers that we had before. So here we're just saying for every combination of row, column, and value. And then we're saying if the proposition is true, then none of the other propositions in that row for that value can be true. And this generator just kind of selects those ones, basically. So the same row, the same value, but not the same column. And yeah, we're saying that none of them can be true. And also we can write the same thing for columns. So this one looks really very similar. We just flip the not up here, and that works. And then we have the final constraint, kind of, which is that they must not appear in the same square. And this also kind of has quite a similar form. So we just define this helper here. So this takes A and B, and this is either across the square or down the square. So it could be a row or a column number. And it just tells you whether, like, for a given pair of rows or columns, whether they're in the same kind of big 3x3 square. And then here it looks quite similar, except the constraint is just that the rows and columns have to be in the same square, and it must not be the same proposition. And we just select out the proposition, and then we're saying yes, exactly. So if the proposition is true, then none of the other propositions for that value can be true. Yes. So there's kind of one more. So at this point, really, we can try and build a model out of this, and kind of we have encoded the rules of Sudoku, but the problem is that a valid solution is to set them all to be false, because all we've said here is kind of if this is true, then these other things must not be true. So it's valid to have nothing true at all, really. So we have to have one more constraint, and that's just that every cell must hold some value. So here we just select kind of for just the value for every cell. So this is in the top left cell, it must have a 1, a 2, a 3, or a 4 up to 9, and then the same for the one across, and then all the way down to the bottom right corner. We say like that must have a value too. And that one looks a bit like this. So we're saying here we're just selecting all the values for a given cell, and then we're saying one of them must be true, at least one of them, and then we're saying that for all cells they must hold a value. So yeah, this is our model. So we just take all of our constraints and we say they must just all be true. And it's just a formula. So this is not doing any magic really. It's just building up a really big, complicated expression like these, just in memory. And it's really big. I mean, with this library, you can't actually print it because it's got too many variables. But there's one more thing we need to do. So this isn't that interesting either, because if we solve this, we'll just find a valid Sudoku. And that actually works, which is quite nice. But what I did is I went on Google and I just typed in world's hardest Sudoku. And there's no internet, but should have thought that through. But I found one, and all we do basically is we just say like the propositions for this partial solution must be true. So for example, there's an 8 in the top left corner, and there's a 3 kind of 3 across and 2 down, and so on. So this is the final thing we get. So I didn't actually show this one because it's quite similar to the others. It's not that interesting. And now what we want to find is what we call a satisfying assignment. So this is basically just the values of x, I, j, k that are true. So there'll be, well, we hope that there'll be one true x, I, j, k for every cell. And then if we extract the value of k, then it will tell us what values are in which cells in the Sudoku. And basically, I think at this point, really I haven't made it any easier, because finding one of these is also really hard. However, the good news is that someone else has written the software to do this for you. So this problem, which is really hard, I mean, you just download some code off the internet and you can just get something to do it, and it's pretty fast as well. So here is kind of my overall solution. If I enter presentation mode, and it's pretty much just like exactly what I showed you. So we generate the props here, and then we say the values in the rows must be unique. The values in the column must be unique. They must be in the same square. And then every cell has a value. Ooh, maybe not that. Every cell has a value. And then this is the bit for the partial solution. And then we generate our model. And then we say, solve the model. And this does actually work, as I can hopefully show you. So if I just do SBT run. This is SBT being very slow. The solver's really fast, trust me. There we go. So it solved the world's hardest Sudoku, and it takes about 100 milliseconds. And I think this will work for all Sudoku, pretty much. I mean, that was the world's hardest one, so the other ones are easier, I think. And basically, I think this is a really nice approach to solving problems, because I think the program that I wrote is actually kind of simple, really. So this is just a formal way of talking about the rules of Sudoku. And I think like everyone understands them because it's like a simple puzzle, and the formalism like isn't that hard to understand. I don't think, and it's just you're writing a program to generate these, and I just don't think that's too hard. And then the hard bit, someone else has already done it, and it turns out these are not useful only for puzzles. So people use them a lot for analyzing programs, for instance. So there's ways of encoding like program flow in propositional logic, and there's even solvers for more complicated logics. So this one, SAT, it's very simple. It only talks about true and false, but we can also introduce like numbers into it. So you can say, find me an x less than 5 such that x squared equals 49. And you just say, find it for me, and it will just go off and do it, which is pretty nice, I think. So I'd really encourage you to like have a play around with it. I mean, I don't think it's too hard to use, and it's definitely a good thing to have in your toolkit if you like solving problems. So the usual spiel about hiring. I work for Football Radar. It's a great company to work for, and we're always hiring people who like Scala. So I would encourage you guys to apply, and there are a couple of us here, so just grab us if you want to talk to us. Has anyone got any questions?
What's the name of that library?
So the question is, what's the name of the library I'm using? So the one I'm using is called CafeSat, so CAFESAT. It's like this. I can get it on the screen.
Is a SAT solver for Scala? Is a SAT solver library?
So the question is the SAT solver library written in Scala? And this one is actually written in Scala, yes. I would say it's probably not the best one. So there's one called Z3, but this one had a really nice Scala DSL, so I used that instead.
So can you solve other Prolog type of problems with this library? Prolog, you know,
Yes, so this is, the question is, can you solve Prolog problems with this library?
yeah, how does it compare with Prolog?
So I think I don't know that much about Prolog, but I think Prolog basically expresses a kind of a form of logic which is different to propositional logic. So I think it's not stronger than propositional logic, and it's also not weaker. There's just different features in it. So, it solves that Prolog, I think. So I think you can express many puzzles in Prolog, and you can also express many puzzles in propositional logic, and you know which one you choose depends on kind of the problem. It's a bit unsatisfying, but that's what I can do, I guess. Yeah.
So, is there a limit? Because generally SATs are NP problem. You can't solve them.
Yes. So the question is there a limit? And SAT is an NP complete and NP hard problem. So in general, you can't solve it. And so this is a really interesting thing, actually. So what was just said there is true. So in general, it takes 2 to the n time to solve a SAT problem. So there's no better approach than brute forcing in general. So obviously, like doing that for Sudoku is intractable, and in the real world, people use SAT for like really, really big problems. So the interesting thing is that although it's 2 to the n time in the worst case, it seems like in the real world, like SAT solvers now are good enough that they don't hit that case. And no one really knows what it is, but it's quite nice, so quite helpful.